Atomic Space Race is an orbital mechanics puzzle game about navigating through realistic star systems and orbital systems to meet certain objectives. Recently, I've made some improvements to the camera systems that I wanted to show off, so let's get into it. We'll play on the moonshot level, which is just a simple recreation of the Earth and Moon, with the objective being to get in close to the Moon at least once. You play the game by placing orders that modify your path, and you can look through the entire timeline of the level to see when you want to make changes. This lets you get a lot of trial and error in an unfamiliar system, since orbital mechanics aren't something that people are very familiar with, by and large. So the first thing that I've added to the camera system lately is the ability to track an object. So what that means is if I go over here and I click on Track Luna, then you can just scroll time, and now instead of sitting still, it follows the motion of the Moon. And you can move the camera around and it will respect that. But that's not the big feature. The big feature is reference frames. I'm maybe using that slightly differently than is strictly accurate in a scientific sense, since it is a term that comes up a lot in relativity and so forth. So let me explain exactly what I mean by that. And that'll help as well if you're unfamiliar with the concept at all. So in space, everything is in motion all the time. The Earth, the Moon orbits the Earth orbits the Sun orbits the galaxy is moving itself. I wouldn't be surprised if it turns out that the universe is moving in some meaningful way. So if you're making a change to something, you have to account for that somehow. For our purposes, the system that you're in is treated as if it's not moving because everything else isn't relevant. But if you get in a situation where you're orbiting the Moon's orbiting the Earth's orbiting the Sun, that could be pretty complicated. Right here we don't have the Sun to worry about, but in other levels we do. So what we can do is cancel out the motion of an object. For example, I can set this to draw everything in reference to the Moon, and now this is what the universe looks like if the Moon is stationary. Everything else is still moving the same that it was before, but it's being drawn differently. So you see the Earth is moving around the Moon, and your ship moving around the Earth. This isn't very useful to us right this second, but it will be momentarily. So let me punch in a maneuver. We're going to burn straight north, straight up, 10 meters a second, about 1 gravity, for 110 seconds. We'll put it in at 90 seconds initially, and I've got a timestamp that I've located earlier that gets us what I want. So you see the marker here that indicates that there is a burn. It's far enough in the future that it doesn't immediately show up, so if we scroll forward, you can see this burn gets us some motion. It pushes our farthest point of the orbit out towards the Moon, but it doesn't get us all the way to the objective. If we draw that in reference to the Moon, it gets a little weird, but you can see that the ship moves like this until it gets there, and we get a little bit closer than we ever were before. If we push this burn further out, take it to 110 seconds, you see that the course now changes. Now, if we are looking at it from the point of view of Earth, here it's hard to see exactly what's going on, whether this is a benefit to us or not. The objective circle turns from orange to blue to show that we have met our objective, so you can see it that way. But if you're trying to refine it piece by piece, say if we put it in at 100 seconds, okay, well, how close does that get us to the Moon? can't really tell from here. You can scrub back and forth on the timeline to see, okay, well that's roughly getting there. But if we draw it from the perspective of the moon, then you can see that this gets closer. If we push it to 109 seconds, or 105 seconds rather, we get even closer, 106, closer still, 107. At that point we actually pass in there. Eventually there should be draggable orders that'll let this be a smoother process of trial and error, but at present you can get there pretty quick. So if we put it at 110, we meet this, and then we cross in here, and that meets the needs of the level, but I want to get in orbit of the moon, so I'm going to have to slow down once I'm inside its sphere of influence, and that'll get us into orbit. And you can see it from here that that's something that's possible, so we're in there. So this frame of reference is useful for that kind of thing. If you're just drawing it from Earth, again, unless you're looking at it at the right time, you can't really tell for certain. There's sort of a telltale here that our course is being pulled by the gravity pretty strongly. But what if we want to be able to see both of those things at once? That's where a more complicated thing comes into play, called the rotating frame of reference. So with a rotating frame of reference, you can do it with just one object and sort of a rotation speed, but to be most useful in most orbital systems, it's going to need two objects. So we've got two. We've got the Earth and the Moon. And what it means is that we're going to be taking both of them into account so that they're at fixed positions relative to each other over the course of time. So let's push this second button here that's going to make the moon be our second point of reference. And now everything's being drawn as if both are stationary. The moon moves back and forth a little bit since it doesn't equalize distances, but in terms of its orbit, it's looked at as stationary. And now if we scroll through time, we see that here you can see both parts. You can see the motion around Earth usefully, and you can see the motion around the moon usefully at the same time. Then once we get to our second order, now as usual with these videos, I found these points in time earlier, so I don't have to trial and error exactly what's going on during the video, but it's not that hard to search them out yourself. It doesn't take very long. So I put that burn there, and it slows us down into Earth or into lunar orbit. And from this frame of reference, you can see both those orbits at the same time. If we look at this just from the Earth, or from the default frame of reference, it looks like this. So it gets kind of weird. And if we look at it from the moon's frame of reference, again, it looks all squiggly from here, and then it gets normal. Now you can extract some meaning from that squiggle once you're used to it, but it's still pretty useful to be able to draw it like this. Now, that's a fairly straightforward use of it. A more complicated situation comes to Lagrange points. So Lagrange points are points in a star system where you can be stable in that circular rotating frame of reference that we were just looking at. So you can be stationary effectively. You can be at a fixed distance, is easier to say, more useful, from two different objects at the same time. I've got a level set up to take advantage of those, so I'll load that now. Here we have this planet of Tigris, rotating or orbiting around its star. We've got you down here, and we've got a station that you need to get close to. Now there's 5 Lagrange points of varying degrees of stability. The ship and the station are at the L4 and L5 points at the start here. So they are at the same position, or at the same orbit roughly as the planet, but ahead and behind it about 60 degrees. Now what's special about these points is that if you're anywhere else in the star system, then you won't be able to maintain a fixed distance from these two bodies at the same time without expending certain amounts of fuel constantly. But at these points, there are forces at work that stabilize your position, so you don't have to actively stabilize. So what we're going to need to do here is change our position in the orbit. So I'm going to lower our position, lower our orbit with a braking burn. Now here, we get one burn, slows us down, and because of the positioning, this doesn't get us where we need to go yet, and you can see that the gravity of the main planet actually moves our orbit around a bunch. We can draw this from reference to the planet, and it's not especially clean, but if we use the circular frame of reference, the rotating frame of reference, you can see where we are in this space a little bit better. So let's actually bump that down to what we need. So now this burn gets us straight to the correct place. And if we look at it without that circular rotating frame of reference, it doesn't really look obvious from this moment in time that that's going to be how it works out. If you scroll through, it works out that way. But inside of that rotating frame of reference, we can see this interesting periodic travel between the 3 different Lagrange points involved. Now the real fun begins with the stability here. Once we're inside of this other Lagrange point, we can break. So we add a new order there. It's 60, 40, 50. We add that braking burn, and that gets us into orbit of the other Lagrange point, which the station that we're supposed to get close to is also orbiting. So at that point, you can see this weird immersion effect here where these objects are orbiting something that isn't even there. There's not a physical body there, creating gravity that they orbit. They're just being stabilized there by the forces of their motion and the gravity of the star and the planet working together. But if you look at that from outside of that frame of reference, that's not really obvious that that's what's going on. You can focus on the ship here, frame it so that we follow it. Zoom in. Sorry, we track it. I framed it, I didn't track it. Track center. And then after this braking burn, it just looks like we're sort of wobbling around in the same area, but it's not clear that that orbit is happening. So that circular frame of reference becomes a very powerful tool for seeing what kind of things are going on. And these Lagrange points are something that you see a lot in science fiction or in planning of potential future space infrastructure or scientific missions. We've put a couple of different observatories and probes at Lagrange points. And the Jupiter Lagrange points are places where you can relatively easily get to a lot of potentially useful asteroids. And that kind of thing is probably going to crop up in other star systems as well. So for a science fiction game, that's a pretty useful thing to be able to model, and it just comes directly out of simulating all the physical forces involved. There's not any special cases or anything that are being implemented. And this is one of the things that the simulation approach gets you that you don't get in simpler approximations that are used in some other games, though not all. So I will just leave it here with, I'm gonna snap back to that circular frame of reference, zoom in on the player ship here, track it again. And I'll just leave it with watching this go until the end of the level, because it's pretty. If I push the right buttons.